One of the things that AI is doing that is extremely helpful is very sophisticated diagnostics. For a long time, we've used computers to read X-ray scans, to look at brain scans. And they are often, if you feed them enough information and relate that to patient data, they are very likely to be able to discern things that, although some very, very good pathologists could see, most cannot. And in some cases, even the pathologists can't, even the very best can't make the determination. They're capable of looking at huge amounts of information. The computers are analyzing it, correlating it to outcomes, and giving you diagnostic information. And that's true for a whole host of instruments. It's not just scanning. It's a lot of the blood tests, a lot of other things. So that's a use. It's helping doctors diagnose and understand what might be wrong with their patients. Now, one of the great revolutions of the last 20, 30 years has been understanding our own genes. So we're going to switch topics now. We're going to look at AI for predicting health. You may have read this year is a year in which there's now a recommendation. The DNA sequencing has become so fast and so accurate that we should begin to test newborns, do the complete DNA sequence of a newborn. And the reason for that is some fraction of them are going to be born with inherent changes in their DNA, which are going to have immediate effects on their survival. Not only that, there are actionable things that can be done to change those health outcomes so that if you detect it as a child is born, it may take 5 or 6 hours at the most to get the information and the recommendation as to what should be done, you can save the lives and change the lives for the better of newborns. Now, a newborn can't give consent to have their DNA sequenced, of course. The parents have to give their consent. And that information will stay around for a lifetime for that person. So that's a potential downside of that. On the other side is the upside. It may save that person's life. It may make sure they have a happy and successful life. That's the first use of that. But it's not the only use. Just this week, it's been announced that 500,000 people in the UK have allowed their DNA to be completely sequenced, along with their lifetime medical record from the National Health Service. That adds to the 200,000 of the Icelandic population. And very soon, another 1 million from the US studies. Who knows who else is doing such studies? These are complete, highly accurate DNA sequences that correlate with health outcomes. We're already beginning to see some of the advantages of those systems. For example, in the Iceland study, by making these correlations and looking at the health and the longevity and of the population, these 200,000 people, and correlating that to their DNA and the changes amongst that population, the AI systems were able to identify 10, in some cases 20 genes that make a difference to lifespan. If you have one of those variants, and you can identify those variants, your life is likely to be years shorter than people that have without that variant. And there's about 10 or 20 of them that are actionable, that actually, if you detect those changes early on, you can change people's lifestyle, give them medications, do other minor changes, and allow them probably to live a normal lifespan. That's called an actionable genetic difference. Does that mean you should rush out and get your DNA analyzed? Well, I recommend that my friends and family do that to see if they have any of these actionable genes. And it's something that's worth thinking about. And that kind of information is going to become more and more available. You couldn't do that with ordinary computer programs. You have to do that with the power that now is available through really smart systems They're able to take huge amounts of data, analyze it, compare and contrast. That is the same kind of tool that's now helping modern biology. Modern biology used to be looking at very individual changes. If I change this, I get this result. However, we've all known if we change A, it's going to change A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. So many changes. Every protein, every gene, everything in a cell and the human body relates to one another. These things are very concentrated. Cells are enormously concentrated, and everything is bumping into everything all the time and changing it. Well, computers are now beginning to be able to understand those very complex networks. And I would say we're at the beginning of that, but we need the power of computation to understand what we're doing. Let me give just a personal experience of what developing this drug is like. I was a CEO of a pharmaceutical company for a while. And we know that most drugs that people test, something like either it's 1 out of 100 or 1 in 10, depends on where the test has got. It doesn't work for some reason. There's a side effect. It doesn't have the effect you want. It has a different effect. And it's because we really don't know enough. In fact, what I kind of liken it is to somebody giving a Roman a car and throwing a rock into the engine and hope it's going to improve it. Well, sometimes it might, maybe 1 out of 1,000 times. So we're a little better than that. We now throw wrenches in to fit specific bolts. And sometimes we could turn a wrench, but we're not sure all the changes that are going to occur. With computation, we're going to get better at that. And we're going to get better at finding the right wrench for the right bolt. We're going to get better at finding the right molecule. In fact, one of the big problems we right now have is that a small molecule that you put into the body that you've designed to stick to a certain protein and change its activity, and that's your drug, actually sticks to a bunch of other stuff too. And computers can help us do that. Computers can help us understand how proteins interact with each other. What the electrostatic surfaces are, what the shapes are. All of that is helping research enormously. Will that have a downside? Well, those people who don't have that skill are going to be at a disadvantage, that's for sure. And one thing that's happening with this new technology is expensive. One thing most of us don't think about is the energy that's used in computation. Many years ago, I realized that these AI farms or these information farms have to be located where there's enormous amounts of energy. In fact, they're located usually where old aluminum smelting plants were along big rivers like the Colorado River. Big rivers because you use the hydroelectric power there to create the electricity. It takes an enormous amount of energy. And as our computational systems get better, it's going to take more and more energy. You can quickly calculate that if we just let the current systems run, they'll be using about 8 to 10% of all our energy. And the systems are getting better and better. So there's a couple of things that people are now thinking about with energy. And we know energy is climate and it's our life too. Can you make computational more efficient? Well, maybe you can do that with quantum computing. People have been trying to get a lot more information out of a little bit of information, or they're trying to use new computer algorithms altogether to do what your own human brain does. You're a very powerful computer and you don't even get very hot. You work at a very low energy level. How do you do that? Not by changing everything into bits of 0 and 1s, but by using your past knowledge and your past experience to select what it is that you think about and how you interpret data. You use past experience to help explain. And there's a lot of people who are thinking about the brain. And actually, one reason we have a lot of false illusions and the brain makes mistakes with these things, it's really just making approximations and it's filtering out a lot of other stuff. Well, there are people who are working on AI and trying to have it do the same thing so you don't use so much energy. There's 3 or 4 different ways around the energy conundrum. One is to produce a lot more energy. through fusion power. Another is to make a computer chip that does more with less energy. And a third is to use a much more clever brain-like analysis to focus in on the problems that are important and not every little bit of data that exists. But one thing for sure, we're going to live in a world which is largely driven by computer power. Now, there's